The morning of November 12, 1942. Richmond, California, 4 days and 15 hours after its keel plates touched the ground, a Liberty ship stood ready for launch. The SS Robert E. Peary had been assembled in less than 5 days, a feat that would capture headlines from Seattle to Boston. But the truth beneath that record reveals something more remarkable than speed. It exposes a quiet revolution in American manufacturing, driven not by engineers in boardrooms, but by shipfitters and welders who had never built a vessel in their lives. At the war's beginning, constructing a single merchant ship required 230 days of labor. Ships had always been built from the keel upward by one crew of workers, a process consuming as long as 6 months. Riveting alone accounted for 1/3 of the labor costs. Each rivet required heating, positioning, and hammering thousands upon thousands of them, driven by skilled craftsmen whose expertise took years to develop. Then came welding, and with it, a problem no one had anticipated. Traditional shipbuilders distrusted the technique. During World War II, there were nearly 1,500 instances of significant brittle fractures in welded ships. 12 vessels, including 3 Liberty ships, broke in half without warning. The SS John P. Gaines sank on November 24, 1943, taking 10 lives with it into the Atlantic. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The question facing America in 1942 was not whether welding could build ships faster. It was whether welding could build ships that would not crack apart in the North Atlantic cold, ships that would survive the journey to deliver the men and materials that would determine whether the Allies could win the war. By 1943, 18 American shipyards were launching 3 Liberty ships every day. 2,710 vessels would be completed between 1941 and 1945, the largest construction program of a single ship design in history, and it depended entirely on a fabrication method that seemed determined to kill the sailors who trusted it. This is the story of how that method was not perfected in laboratories or design offices, but on the shipyard floor itself, by workers who understood that their brothers, their sons, their husbands would sail on what they built, workers who invented solutions the engineers had not imagined. Workers like Garrie Thompson, an assembly worker at Richmond Yard No. 2, who created a device that would save 5,000 man-hours per ship and help turn the tide of a global war. But first, we must understand what they were up against. Part 2. Building the World. The Context. The Liberty ship was British in conception, developed from designs created to replace merchant vessels lost to German U-boat attacks. Even before the United States officially entered World War II, Atlantic and Pacific coast shipyards were already building these cargo vessels. Britain was hemorrhaging tonnage faster than it could replace it. The Battle of the Atlantic was not a battle of grand naval engagements, it was a battle of arithmetic ships sunk versus ships built. The man who would revolutionize American shipbuilding, Henry J. Kaiser, had never constructed a ship in his life until 1940. His company had been the prime contractor for the Hoover Dam, the Bonneville Dam, the Grand Coulee Dam, and the San Francisco-Oakland Bay Bridge. He understood concrete and steel, schedules and logistics. But ships were different. Or so everyone believed. The Liberty ship design was designated EC-2SC-1, emergency cargo, sized between 400 and 450 feet in length, steam-powered. They were designed to carry 10,000 long tons of cargo, though during wartime, they generally carried loads far exceeding this capacity. These were not sophisticated vessels. They used a 140 short-ton vertical triple-expansion steam engine of obsolete design, selected because it was cheaper and easier to build in the numbers required, and because more companies could manufacture it than could produce the precise steam turbines used in modern ships. The Liberty ship was, by every measure, a compromise. A vessel built not to impress, but to survive long enough to cross an ocean once, perhaps twice. The ships were constructed to last about 5 years. Expendable tools of war, but to build them in the quantities needed, Everything about traditional shipbuilding had to change. Kaiser adapted mass production techniques to shipbuilding, instituting modular construction in which ship sections were welded together instead of riveted. The concept of building components in separate facilities and bringing them together to assemble quickly was something shipbuilders had been dreaming about for decades. Kaiser would make it reality. Each Liberty ship required nearly 50 miles of welding. Welding could be done much faster than riveting, and welders could be trained quickly. A complete novice could become productive in little more than a week. Welding required less upper body strength than riveting, which meant that women could undertake the work. Approximately 1.8 million Americans were employed in Liberty shipyards during the war. This was the revolution Kaiser brought, not just speed, but democratization. The skilled craftsmen who had dominated shipbuilding for generations were being drafted into military service. Kaiser needed bodies, any bodies willing to work. He needed grandmothers and teenagers, farmers and store clerks. He needed people who had never seen an ocean, much less built a vessel to cross one. And he needed them to build ships that would not break apart and sink. The prevailing engineering doctrine held that welding was inherently risky for large structures. Riveted ships had connected steel plates in a way that prevented cracks from propagating across joints. Welded construction, by contrast, allowed cracks to run large distances unimpeded. When a rivet failed, it failed alone. When a weld failed, the entire structure could unzip. Investigations after early fractures focused on the shipyards themselves, which often used inexperienced workers and new welding techniques to produce large numbers of ships in great haste. But Cambridge University researcher Constance Tipper demonstrated that the fractures were not initiated by welding defects, but by the grade of steel used, which suffered from embrittlement in the cold temperatures of the North Atlantic. The steel itself changed from ductile to brittle at certain temperatures, and the welded construction simply allowed those failures to cascade. One common type of crack originated at the square corner of a hatch that coincided with a welded seam, with both the corner and the weld acting as stress concentrators. This was the world Kaiser's workers entered, a race against time, using a construction method that killed ships, employing workers who had never held a welding torch, all to feed a war machine that consumed vessels faster than any shipyard had ever produced them. The doctrine said it could not be done. The mathematics said Britain would starve before America could build enough tonnage to matter. The workers on the floor would prove both wrong. Part 3. The Human Element. Innovation from the Ground. By 1944, Kaiser's Richmond shipyards routinely completed a Liberty ship in little more than 2 weeks. The 4 Richmond Kaiser shipyards built 747 ships during World War II, completing them in 2/3 the time and at 1/4 the cost of vessels built elsewhere. How? The answer lies not in a corporate strategy or engineering brilliance, but in the accumulated wisdom of thousands of workers who understood that small improvements, multiplied across hundreds of ships, could alter the course of history. Garrie Thompson, an assembly worker at Richmond Yard No. 2, invented a tool called the jackbacker. The device allowed a single shipfitter to draw 2 steel plates together for welding. Shaped like a cast-iron femur with a giant bolt down its axis, it eliminated the 1,200 disposable clips that customarily held deck plates in position during welding. 1,200 clips per ship, each one requiring installation and removal, each one adding weight, consuming steel, demanding labor. Thompson's jackbacker saved thousands of pounds of steel and cut 5,000 man-hours per ship. 5,000 hours per ship. Multiplied across the 247 Liberty ships built at Richmond Yard No. 2 alone, Thompson's innovation saved more than 1 million man-hours. One man, one idea, one tool that looked like a bone and functioned like a revolution. But Thompson was not alone. Another Richmond worker devised a little prefab plant where crews prefabricated and assembled the precision-cut plates, forming the foundation of Liberty ship steam engines, trimming the time needed for final installation by almost 90%. Altogether, the Maritime Commission received more than 3,000 improvement suggestions during the war, which collectively saved $45 million and 31 million labor hours. 31 million hours. 600,000 hours per shipyard across the 18 facilities building Liberty ships, the equivalent of adding 340 workers labouring full-time for an entire year at every single shipyard. These were not engineers with degrees. These were not managers with titles. When yard manager Clay Bedford was asked about the record-setting construction of the SS Robert E. Peary, he told the United Press Association that the real accomplishment came from empowering employees to innovate. We are not primarily trying to break records. Our main purpose has been experimenting in new prefabrication methods and, after receiving hundreds of valuable suggestions and time-saving inventions from our workers, we decided to try them all on one hull and see what would happen. What happened was a ship built in less than 5 days. What happened was a construction program that turned out cargo vessels faster than German submarines could sink them. What happened was the transformation of industrial warfare. The Richmond shipyards employed women extensively, workers affectionately called Wendy the Welders, though the more famous nickname Rosie the Riveter persisted despite the fact that Kaiser's yards used almost no riveting at all. Some payrolls comprised as many as 50% black workers and 10% women. They came from farms in Oklahoma, from segregated neighborhoods in Oakland, from small towns across America where the only ships they had seen were in newsreels. And they learned to weld steel plates that would carry their brothers across oceans infested with submarines. The innovation was not in the grand design. The Maritime Commission's standard cargo ships designed before the war already used welded construction. The innovation was in 10,000 small acts of problem-solving performed by people whose names history would not record. Workers who saw that 2 plates could be drawn together more efficiently. Workers who realized that prefabricating an engine foundation would eliminate hours of fitting work. Workers who understood that their illegal trick was simply finding a better way. The title promised you a story about how Liberty ships launched in 72 hours instead of 6 months. The truth is more complex and more profound. The first Liberty ship, the SS Patrick Henry, required 244 days to build in 1941. By 1943, the average construction time had dropped to 42 days. The SS Robert E. Peary's 4-day construction was a propaganda effort, a competition between yards to demonstrate that America could produce ships faster than they could be sunk. Much fitting out and other work remained to be done after the Peary was launched, and the ship was not delivered for service until November 15th, 7 days and 14 hours after the keel was laid. But the record was never the point. The point was the system that made such speed possible not once, as a stunt, but 3 times every day for years. The point was the workers who made it happen, whose innovations accumulated into industrial, might sufficient to feed armies, supply nations, and turn the arithmetic of the Atlantic in favor of the Allies. 1 in 26 merchant mariners died during the war, a higher fatality rate than any branch of the armed forces. They sailed on ships welded together by people who had learned the trade in a week. They trusted their lives to innovations developed on shipyard floors by workers using tools they had invented themselves. And those ships held, most of them. More than 2,400 of the 2,751 Liberty ships built survived the war. The welders knew what they were building. They knew who would sail on it. Many workers recounted how important their jobs were and how careful they were in their welding, realizing that the lives of their husbands, brothers, and sons depended on the cargoes delivered by these ships. Garrie Thompson's jackbacker was not an illegal trick. It was ingenuity born of necessity, refined by repetition, and multiplied across a construction program that changed naval warfare forever. Ships today avoid rectangular corners and use new types of steel with higher fracture toughness, and more educated welders produce welds with fewer flaws. The lessons learned from Liberty ship failures led to innovations that allow safer shipbuilding today. But in 1942, on the floor of Richmond Shipyard No. 2, those lessons had not yet been learned. The ships were cracking, the steel was brittle, the workers were inexperienced. And they built 747 vessels anyway, faster and cheaper than anyone thought possible, because when your brother is crossing the Atlantic in a ship you welded, you find a way to make it work. That is the illegal trick. Not welding itself, but the audacity to believe that ordinary people, given extraordinary circumstances, could reinvent an entire industry in the time it takes to fight a war. They did, and the ships they built brought liberty to Europe. Part 4. The deep dive to the specifications of failure. For the original Liberty ship design, the rate of Class I casualties, fractures that endangered the ship or resulted in its loss, was 4.3 per 100 ship years. To understand what that number meant, one must first understand what it measured. A ship year is a unit of operational exposure. One vessel sailing for 12 months equals one ship year. 10 vessels sailing for 36 days each equals one ship year. Before the war, the loss rate from all causes for merchant vessels was 1 per 100 ship years. The Liberty ships were failing from structural defects alone at more than 4 times the pre-war total loss rate. By April 1943, more than 100 Class I and Class II casualties had already occurred. 4 ships had actually broken in two. In January 1943 alone, about 20 ship failures occurred, with 4 or 5 suffering Class I damage or total hull failure. The workers building these vessels knew the statistics. They read the newspapers, they heard the stories from returning sailors, and they continued welding. 52% of all serious fractures on Liberty ships originated at the corners of cargo hatches. This was not a mystery to the engineers. At the start, there was virtually no experience with welded ships, and there were built-in stress concentrations, notably at square hatch corners, at the end of bilge keels, and at cutouts in the shear strakes. These discontinuities were the origin of most serious brittle fractures. But why corners? Why did a 90-degree angle become a death sentence? Stress concentration. When force is applied to a structure, that stress distributes across the material. A smooth curve allows stress to flow. A sharp corner forces stress to accumulate. In brittle materials, there exists a critical combination of stress and crack length, leading to unstable crack growth and catastrophic failure. The corner of a hatch, welded to the deck plates, created exactly that combination. Brittle fractures are characterized by rapid crack propagation, which occurs at sonic speed and perpendicular to the direction of applied tensile stress. Sonic speed. The crack moved faster than sound through steel. By the time a sailor heard the ship breaking, the fracture had already traveled the length of the hull. Plates in which brittle failures originated had a 21 joule transition temperature of 15 to 65 degrees Celsius, with a mean of 40 degrees Celsius. Translation: the steel used in Liberty ships became notch brittle, susceptible to sudden fracture when a crack or notch was present at temperatures well above freezing. Such steel would undoubtedly have been notch brittle during winter and spring in the North Atlantic. The North Atlantic in winter. Water temperatures hovering near freezing. Air temperatures below 0 degrees Celsius, waves 30 feet high, and steel that became brittle at 40 degrees Celsius, 104 degrees Fahrenheit, warmer than a spring day. The loss rate became serious in the winter and spring of 1942 to 43 and peaked during the same period of 1943 to 44, the coldest months, when convoys to Britain faced not only U-boats and storms, but the possibility that their own ships would simply crack open and sink without any external cause whatsoever. By 1947, approximately 60 United States ships, roughly 50% of them. Liberty ships required structural component replacement due to fractures that occurred when exposed to operating temperatures below 5 degrees Celsius. 60 ships, hundreds of cracks, thousands of sailors trusting their lives to hulls that were disintegrating around them. The training that prepared welders for this work lasted at most a few weeks. A complete novice could be trained to be a productive welder doing the simplest tasks in little more than a week. From never having held a welding torch to being responsible for seams that would face the North Atlantic in winter, the welding process itself created additional problems. Beyond cracks, another important reason for failure associated with welding was hydrogen embrittlement. When moisture in the welding rod or on the steel surface decomposes in the heat of the arc, it releases hydrogen. That hydrogen becomes trapped in the cooling weld, making the metal even more prone to cracking. Inexperienced welders, working at speed, using rods that might not have been stored properly in damp coastal air, were unwittingly embedding time bombs into every seam. The specifications called for impact testing of the steel. During the construction period, there was considerable discussion about the means of avoiding brittle fracture and, in particular, about the level of impact energy to be specified for plate material. Eventually, the figure of 25 foot-pounds at 0 degrees Celsius was established as the basic requirement, but specifications are one thing, implementation under wartime pressure is another. Steel mills were running at capacity. Shipyards were demanding material, faster than quality controls could keep pace, and the men and women doing the welding had no way to test the plates they were joining. They simply had to trust that what they were given would hold. One of the vessel service failures was the famous 1944 failure of two storage vessels that released large volumes of liquefied natural gas into the Cleveland sewer system and resulted in fires and explosions that caused the death of 128 people. The same brittle fracture problem that plagued Liberty ships was killing civilians at home. The same steel, the same welding, the same fatal combination of cold temperature and stress concentration, and yet the ships kept launching. Between 1939 and 1945, 5,777 merchant ships were built, compared to just 71 between 1930 and 1937, an 80-fold increase in production. Mass production on a scale never before attempted in shipbuilding. The workers at Richmond and Portland and Baltimore understood what they were building. They understood that corners created stress concentrations. They understood that cold weather made steel brittle. They understood that their welds needed to be perfect because imperfect welds in cold water could propagate cracks that would split a ship in half at sonic speed, and they kept welding. Because the alternative was worse. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The German U-boats were sinking Allied merchant vessels faster than traditional shipbuilding could replace them. The problem was that it was necessary to build merchant ships faster than German Navy submarines could sink them in order to supply the United Kingdom and sustain its war effort. Every day of delay meant more tonnage at the bottom of the Atlantic. Every ship that failed to launch meant less food in Britain, fewer supplies for the armies in Europe, fewer bombs to drop on German industry. The workers knew this. They read it in the newspapers. They heard it in the radio broadcasts. They saw it in the faces of the sailors who came to the shipyards, men who would sail on what they built. So they welded, despite knowing the steel was brittle, despite knowing their training was inadequate, despite knowing that somewhere, in some North Atlantic winter, one of their welds might fail and a ship might break and men might die. They welded because the mathematics of war demanded it. Better to build ships that might fail than to build no ships at all. Better to send convoys with a 4.3% casualty rate from structural defects than to send no convoys and let Britain starve. This was the deep reality beneath the innovation. The jackbacker and the prefabrication and the assembly line techniques were not just about speed and efficiency. They were about building enough ships, fast enough, to overcome both U-boats and the inherent flaws in the ships themselves. The shipyard workers were not ignorant of what they were doing. They were making a calculated sacrifice, accepting known defects in pursuit of overwhelming numbers. And the numbers worked, most of the time. But not always. Part 5. The Climax, When Steel Screams. At 10:30 in the evening on January 16, 1943, an explosive boom shattered the cold night that had settled over the Swan Island shipyard outside Portland, Oregon. The sudden break of the ship's hull could be heard nearly a mile away. Workers throughout Portland heard it. Citizens in their homes heard it. Almost everybody in Portland heard the bang. When they came out to look, they found the middle of the ship up in the air and the ends down in the water. The SS Schenectady was moored at the fitting dock at Swan Island, in calm weather, shortly after returning from her sea trials. Without warning, and with a noise audible for at least a mile, the hull cracked almost in half, just aft of the superstructure. Calm weather. No storm, no collision, no torpedo, The ship simply broke. The cracks reached down the port and starboard sides almost to the keel, which itself fractured, jackknifing upwards out of the water as the bow and stern sagged to the bottom of the river. Only the bottom plates of the ship held. The vessel jackknifed, hinging on the bottom plate, which had remained intact, and the central part of the ship rose clear of the water. It was 11 at night, on a cold night in the low 20s, or possibly lower, cold enough that Portlanders in the southeast quarter of the city were actually ice skating on Laurelhurst Lake. The water in the river was right around 40 degrees. The Schenectady was not a Liberty ship. She was a T2 tanker, 523 feet long and 68 feet wide, compared to Liberty ships at 441 by 57. The keel of the Schenectady was laid on July 1, 1942. The completed hull launched on October 24, and she was declared completed on December 31, 6 months after construction began and 2.5 months ahead of schedule. It was the first ship off a brand-new Henry Kaiser assembly line shipyard on Swan Island, just like the assembly line shipyards that were already cranking out thousands of Liberty ships, only set up to build a bigger model, the pride of Portland. The demonstration that American industrial might could produce not just cargo vessels, but sophisticated tankers capable of carrying 7.5 million gallons of fuel across oceans. And it broke, at dock, in calm weather, 16 days after being declared complete. This was not the first of the war-built merchant fleet to fracture in this way. There had been 10 other major incidents, and several more would follow. But the Schenectady was different. It broke in front of the city, in front of the workers who built it, in front of the nation that was depending on these ships to win the war. In March, another tanker, the SO Manhattan, split in half while entering New York Harbor. Not at sea, not in a storm. While entering harbor, where it should have been safe. The pattern was undeniable. During the winter of 1942-43, 2 cargo vessels located in the North Atlantic, 1 tank vessel off the coast of New York, and the Schenectady and similar tankers at docks in Oregon snapped completely in two following their sea trials. At all 3 locations, water temperatures averaged from approximately 0 degrees Celsius to 7 degrees Celsius, with air temperatures ranging from approximately -2 degrees Celsius to 5 degrees Celsius. Cold. But not Arctic cold, just winter cold. The kind of cold that was routine for ships crossing the North. The official investigation moved swiftly. United States Coast Guard engineers who studied the incident at the time concluded that faulty welds were the culprit. The explanation fit the available evidence. Welded construction was new, the workers were inexperienced, the production pace was frantic. Of course the welds were failing, but that explanation, comforting in its simplicity, was wrong. The Ministry of War Transport borrowed the British-built Empire Duke for testing purposes. Constance Tipper of Cambridge University demonstrated that the fractures did not start in the welds, but were due to the embrittlement of the steel used. When used in riveted construction, the same steel did not have this problem. Tipper discovered that at a certain temperature, the steel the ships were made of changed from being ductile to brittle. The steel itself was the problem. Not the welding technique, not the workers, not the training. The fundamental material being used to build ships that would operate in cold water became brittle in cold water. The John P. Gaines was assembled at the Oregon Shipbuilding Corporation in Portland in July 1943. On its way from Dutch Harbor in the Aleutian Islands to Seattle, less than 6 months after its completion, the vessel fractured as air temperatures hovered around 0 degrees Celsius and a large swell washed over the port bow. The crack propagated not along welds, but straight through the plating. Ultimately, the ship completely split in 2 parts. Its bow presumably sank, while the stern drifted ashore in Alaska, through the plating, not along the welds. The Schenectady's cracks travelled through solid steel, not along welded seams. The fractures that engineers blamed on inexperienced welders were actually traveling through the base metal that no welder had touched. Historians have documented 19 Liberty ships as having split in two without warning, 19 complete structural failures. 12 ships, including 3 of the 2,710 Liberty ships built, broke in half without warning, including the SS John P. Gaines, which sank on November 24, 1943, with the loss of 10 lives. 10 lives. Men who woke up that morning expecting to reach Seattle. Men who trusted that the ship carrying them across the Pacific would not simply break beneath their feet. Men whose deaths were caused not by enemy action, not by storm or collision, but by the material properties of steel in cold water. The moment of recognition must have been devastating for the engineers and managers who pushed for maximum production speed. They had blamed the workers, they had blamed the welding technique, they had implemented additional training, stricter inspection protocols, better supervision, and ships kept breaking, because the problem was not in the execution, the problem was in the design, in the material selection. In the fundamental assumption that steel strong enough at room temperature would remain strong in the North Atlantic winter. After the severe winter of 1943–44, the design was improved by reducing the severity of notches and by introducing a minimum of 4 riveted seams running the length of the hull and intended as crack arresters. It had been observed that fractures were generally stopped by perpendicular barriers, such as riveted or especially strong seams. Riveted seams, the old technology that welding was supposed to replace, the labor-intensive method that took months instead of weeks, that technology, properly placed, could stop cracks from propagating through welded hulls. The solution was not to abandon welding. The solution was to combine it with carefully placed riveted sections that would act as crack arresters, barriers that would prevent a fracture from unzipping the entire length of a ship. The gunwale bars and other retrofits were successful. No ship with gunwale bars ever failed in service. Through the end of the war, only 127 of the 4,694 Liberty ships and T2 tankers ever suffered a Class I fracture, and no ships with anti-fracture devices failed. No ship with crack arresters ever failed. Not one. The fix worked completely. But it took the Schenectady breaking at dock, the SO Manhattan splitting in harbour, the John P. Gaines sinking with 10 men aboard, and 19 total ships breaking in half to force that recognition. Part 6. The Resolution. What welding actually taught. The Schenectady was repaired and successfully entered service in April 1943. Water was pumped into the compartments amidships so that the entire hull could settle onto the river bottom. Then scab steel was welded across the breach to hold her together, and she was refloated. Towed to a dry dock, she was put back together with a heavy reinforcing plate across the spot where the crack had opened, and was out moving gasoline across the Atlantic Ocean just a few months later. The ship that broke at dock and became infamous throughout the maritime world sailed successfully for the rest of the war and beyond. She sailed to Australia, the Persian Gulf, New Zealand, the Marshall Islands, then Curaçao, back through the Panama Canal to the Marshall Islands, the Caroline Islands, the Admiralty Islands, and finally Ulithi, before returning home to San Pedro, arriving on May 20, 1945. She participated in battle engagements in the Marshall Islands and at Ulithi. The repairs worked. More importantly, the lessons learned worked. It took engineers nearly half a century to determine why the SS Schenectady, while docked quietly in a harbour off Portland, Oregon, one day, suddenly snapped in half. Because the field of fracture mechanics wasn't well understood in the 1940s, the real cause wouldn't be fully comprehended until much later. But the shipbuilders did not have the luxury of waiting 50 years. They had a war to win, so they implemented solutions based on observation rather than complete understanding. They rounded the hatch corners to reduce stress concentration. They installed riveted crack arresters. They improved steel quality as much as wartime production allowed. And they kept building ships. The Schenectady's builder, Kaiser Shipyards, resolved the problem and went on to build an estimated 500 additional ships for the war. None of those ships were reported to have a brittle fracture incident. 500 ships, 0 fractures. The system worked once the necessary modifications were made. In spite of these failures, the Liberty ship program was considered a success for several reasons. The primary reason being that ships that survived failure were able to supply Allied forces in the theatre of operations and, in all likelihood, shortened the war. In addition, structural steels were developed with vastly improved resistances to catastrophic brittle fractures. Detailed analyses of these failures advanced the understanding of crack formation and growth, which ultimately evolved into the discipline of fracture mechanics. The failures created a new field of engineering. Fracture mechanics, the study of how cracks form, propagate, and can be arrested in materials under stress, emerged directly from investigating why Liberty ships broke. Fracture mechanics as an engineering subject started around November 24, 1943, the day the Liberty ship John P. Gaines sank with the loss of 10 lives. 10 lives purchased the knowledge that would save thousands more. The cruel mathematics of wartime innovation. The title of this story promised you an illegal trick that made Liberty ships launch in 72 hours instead of 6 months. The reality is more nuanced and more profound. The trick was not illegal, it was revolutionary. Welding replaced riveting. Prefabrication replaced traditional keel-up construction. Mass production replaced artisanal craftsmanship. And workers like Garrie Thompson invented tools that made the impossible merely difficult. But the true story is not about speed. It is about learning. About a nation that built ships so fast it outpaced its own understanding of the materials being used. About workers who kept welding even after ships started breaking because stopping meant losing the war. About engineers who implemented solutions based on observation when theory could not keep pace with necessity. Ships today avoid the use of rectangular corners to avoid stress concentration. New types of steel were developed that have higher fracture toughness, especially at lower temperatures. In addition, more talented and educated welders can produce welds without, or at least with fewer flaws. Every modern ship benefits from what the Liberty ship program taught. Every welded structure, bridges, buildings, pressure vessels, pipelines incorporates lessons learned when 19 vessels broke in half, and engineers had to figure out why. The Schenectady broke on January 16, 1943. By April, she was repaired and in service. By the end of the war, every ship launched included design modifications to prevent similar failures. The system learned, adapted, survived. That is the illegal trick, if there ever was one. The audacity to build faster than you fully understand, the wisdom to learn from catastrophic failure, and the determination to keep building even when ships break at dock in calm weather because the alternative is surrender. Garrie Thompson's Jack Backer saved 5,000 man-hours per ship. The crack arresters saved uncounted lives. The rounded hatch corners eliminated the stress concentrations that killed the John P. Gaines crew. None of these innovations came from textbooks or engineering schools. They came from people on the shipyard floor who observed, experimented, and refused to accept that the way things were done was the only way they could be done. More than 2,400 of the 2,751 Liberty ships built survived the war. They delivered the food, fuel, ammunition, and troops that liberated Europe. They sailed through North Atlantic winters and Pacific typhoons. Most of them held together because workers who learned to weld in a week cared enough to make their welds perfect, because engineers implemented crack arresters when theory failed, and because a nation chose overwhelming production over cautious perfection. The illegal trick was believing it could be done at all, and then doing it anyway. Part 7. Aftermath. The ships that refused to die. The last Liberty ship built was the SS Albert M. Bow, launched on September 26, 1945, and delivered on October 30, 1945. She was named after the chief engineer of a United States Army freighter who had stayed below decks to shut down his engines after an April 13, 1945 explosion, an act that won him a posthumous Merchant Marine Distinguished Service Medal. The war in Europe had already ended. Japan would surrender within weeks of the bow's launch. The emergency that created the Liberty ship program was over. During the design's production life, 2,751 vessels were built. About 200 of them were lost during the war to various reasons. 200 lost, 2,500 survived. The arithmetic worked. The Liberty ship was considered a 5-year vessel, an expendable, if necessary, material of war, because it was not able to compete with non-emergency vessels in speed, equipment, and general serviceability. 5 years. They were designed to last long enough to win the war and then be scrapped. However, Liberties ended up doing well, plodding the seas for nearly 20 years after the end of World War II. 20 years, 4 times their designed lifespan. The ships that were supposed to be expendable became the backbone of post-war merchant fleets worldwide. Roughly 2,400 Liberty ships came out of the war in serviceable condition. Of these, the Maritime Commission planned to use just over 800 as the backbone of the American merchant fleet. 624 ships were sold to European shipping lines, with over 500 being purchased by Greek shippers. Among those Greek buyers was a young entrepreneur named Aristotle Onassis, who would use surplus Liberty ships to build a shipping empire. The rest entered reserve fleets. The majority entered United States reserve fleets in anchorages at Suisun Bay in California and Philadelphia. Others entered reserve fleets in the James River in Virginia, the Hudson near Tarrytown, New York, and other locales. Hundreds of ships, mothballed in neat rows, waiting for the next emergency. That emergency came in 1950. Many Liberty ships were placed in the reserve fleet, and several supported the Korean War. Ships made 9 trips to the Far East between November 1950 and December 1952 during the Korean War, to equip American troops fighting Communist North Korea. The expendable ships, designed to last 5 years, were still carrying troops and supplies 5 years after the war they were built for had ended. The same was true during the Vietnam War, where Liberty ships continued to serve as valuable transport vessels, 20 years after their design, still sailing, still carrying cargo, still doing the job they were built for in a war their designers never imagined. In the 1950s, the United States Department of Agriculture purchased surplus grain and stored it in the holds of several Liberty ships, anchored in the reserve fleets. The ships that once carried ammunition to Europe became floating grain elevators. The cargo holds that delivered tanks to Normandy stored wheat in American rivers. But by the 1960s, their time was ending. Their use as a major cargo carrier was limited due to their lack of speed. The emergence of containerized shipping sounded their death knell. Modern cargo ships moved faster, carried more, loaded and unloaded in hours instead of days. The Liberty ships, revolutionary in 1942, were obsolete by 1965. In 1965, more than 180 Liberty ships sat at anchor in the reserve fleet in the Hudson River. By 1971, all had been scrapped. The more than 500 Liberty ships held in reserve in California in the early 1960s went to scrapyards beginning that decade. 500 ships, thousands of tons of steel, cut apart and melted down, their metal recycled into cars and buildings and new ships that would never know they were made from the vessels that won a war. Some found unusual second lives. The SS John W. Brown became a vocational high school training ship in New York City for many years. By late 1956, the decline of the American merchant marine, budget problems in New York City, and the expense of maintaining, repairing, and operating the John W. Brown created financial difficulties for the high school. Continuing budget problems finally led to the school closing in mid-1982. By the 1980s, nearly all were gone. The largest class of ships ever built to a single design, reduced to 2 operational survivors. Only 2 operational Liberty ships, SS John W. Brown and SS Jeremiah O'Brien, remain. Both are museum ships that still put out to sea regularly. In 1994, Jeremiah O'Brien steamed from San Francisco to England and France for the 50th anniversary of D-Day the only large ship from the original Operation Overlord fleet to participate in the anniversary, one ship, out of the thousands that crossed the Atlantic, out of the fleet that made the Normandy invasion possible. One ship returned to mark the anniversary, powered by the same obsolete triple-expansion steam engine installed in 1943, welded together by workers who learned their trade in a week. The SS John W. Brown still gets underway several times a year for 6-hour living history cruises through Baltimore Harbor, down the Patapsco River, and into the Chesapeake Bay. Each cruise includes tours of the ship, discussions of the role of the United States Merchant Marine, Liberty ships, and American women in World War II, reenactments of the activities of the ship's World War II, United States Navy, Armed Guard, and flybys and simulated attacks on the ship by World War II aircraft. 2 ships remain operational. A third, the SS Hellas Liberty, exists as a static museum in Greece. That is the physical legacy. 3 vessels out of 2,751, 0.1% survival rate. But the true legacy was never in the ships themselves. Part 8. Legacy. The welds that changed everything. The Liberty Ship program transformed American industry in ways that extended far beyond shipbuilding. During World War II, volunteer merchant mariners who served numbered nearly 250,000, over 9,000 died. Merchant sailors suffered a greater percentage of fatalities, 3.9%, than any branch of the armed forces, higher casualties than the Army, higher than the Navy, higher than the Marines. The men who sailed on Liberty ships faced U-boats, mines, aircraft, and the possibility that their own vessel might crack in half beneath them. 1 in 26 merchant mariners died during the war, and they were civilians, volunteers, men who could have worked in factories at home but chose instead to sail on welded ships across oceans where German submarines hunted them. They sailed because the ships existed. And the ships existed because workers like Garrie Thompson invented better ways to build them. The connection is direct. Thompson's jackbacker saved 5,000 man-hours per ship. Multiply that across hundreds of vessels, and you have tens of thousands of hours redirected toward building additional ships. More ships meant more cargo delivered. More cargo delivered meant better supplied armies. Better supplied armies meant shorter war. Shorter war meant fewer deaths. The mathematics are impersonal, but behind each calculation stood a person, a welder who mastered her craft in a week, a shipfitter who invented a tool that looked like a bone, an engineer who recognized that riveted seams could stop cracks from propagating, a researcher who proved that cold temperature changed steel from ductile to brittle. Their individual contributions accumulated into industrial transformation. The welding techniques developed for Liberty ships became standard practice throughout American manufacturing. The massive increase in production was possible in large part because of a change from riveted to electric arc welded construction. Shipyards were organized for maximum efficiency around the welding process. After the war, those same techniques built bridges, buildings, pipelines, and pressure vessels. The knowledge gained from Liberty ship failures prevented catastrophic fractures in civilian infrastructure for decades. Structural steels were developed with vastly improved resistances to catastrophic brittle fractures. Detailed analyses of these failures advanced the understanding of crack formation and growth, which ultimately evolved into the discipline of fracture mechanics. An entire field of engineering emerged from investigating why ships broke. Universities teach courses in fracture mechanics today. Engineers design structures using principles discovered when the Schenectady split at dock and the John P. Gaines sank in the Pacific. The Liberty ships taught that speed of construction, while valuable, must be balanced against material science. They taught that corners concentrate stress and that cold temperature changes material properties. They taught that welded construction requires crack arresters. They taught that inexperienced workers, properly trained and motivated, can accomplish tasks that experts deemed impossible. Most importantly, they taught that failure, properly analyzed, advances knowledge more than success ever could. The Schenectady broke, was repaired, and sailed successfully for years. The lesson was not that welded ships were doomed, The lesson was that welded ships required design modifications that riveted ships did not. That lesson, learned at the cost of 19 complete hull failures and hundreds of lesser cracks, saved countless structures from similar fates in the decades that followed. Of the approximately 2,700 Liberty ships, 17 were named for outstanding African Americans. The first, in honor of Booker T. Washington, was christened by Marion Anderson in 1942. Captain Hugh Mulzac, an African American, served as master of the ship for 4 years, delivering troops and supplies to the war zones. Captain Hugh Mulzac became the first African American merchant marine naval officer to command an integrated crew during World War II. He earned his captain's rating in the Merchant Marine in 1918, but racial prejudice denied him the right to command a ship. Later, Mulzac was offered the command of a ship with an all-black crew. He refused, declaring that, under no circumstances will I command a Jim Crow vessel. 22 years passed before Mulzac would again receive an offer to command a naval ship. During World War II, his demand for an integrated crew was finally met, and he was put in command of the SS Booker T. Washington. With its crew of 18 nationalities, the Booker T. Washington made 22 round-trip voyages in 5 years and carried 18,000 troops to Europe and the Pacific. On the day his ship was launched, Mulzac recalled, "Everything I ever was, stood for, fought for, dreamed of, came into focus that day. The concrete evidence of the achievement gives one's strivings legitimacy, proves that the ambitions were valid, the struggle worthwhile." The Liberty ships broke racial barriers while breaking speed records. Women welded them, African Americans commanded them, 18 nationalities crewed them. The same emergency that demanded faster construction demanded broader participation. The same desperate need that accepted inexperienced welders accepted previously excluded populations. Progress emerged not from enlightenment, but from necessity, though the progress proved real nonetheless. The ships themselves are mostly gone, but the changes they forced upon American society and American industry remain. Every modern welded structure incorporates lessons from Liberty ship failures. Every diverse workplace reflects doors opened by wartime labor shortages. Every rapid construction project draws from techniques pioneered in Kaiser's shipyards. The legacy is not in the steel. The legacy is in the knowledge. Part 9, Reflection. The true illegal trick returned to the beginning. November 12, 1942. Richmond, California. The SS Robert E. Peary, ready for launch after 4 days and 15 hours of construction. We began with a promise to reveal how one welder's illegal trick made Liberty ships launch in 72 hours instead of 6 months. The promise was hyperbole, like all good titles. But beneath the exaggeration lies a profound truth about how revolutions actually occur. There was no single illegal trick. There was no lone genius whose invention changed everything. What changed everything was the accumulated effect of 3,000 improvement suggestions implemented across 18 shipyards over 4 years. What changed everything was Garrie Thompson's jackbacker saving 5,000 man-hours per ship, multiplied by the little prefab plant reducing engine installation time by 90%, multiplied by 17 banks of welding machines per hull, multiplied by prefabricated deck sections, multiplied by complete outfitting of deck houses before assembly, 3,000 improvements, 31 million labor hours saved, not through grand strategy, but through workers observing inefficiencies and inventing solutions. The illegal trick, if one existed, was believing that ordinary people could reinvent an entire industry in the time it takes to fight a war. That belief violated every principle of traditional craftsmanship. Shipbuilding was an art passed down through generations of apprenticeship. You did not learn it in a week. You did not build ships in sections and weld them together. You did not replace skilled riveters with novice welders and expect the vessels to survive Atlantic crossings. Except they did, mostly. The ships that broke taught as much as the ships that survived. The Schenectady split at dock and proved that cold temperature changes steel properties. The John P. Gaines sank and proved that cracks propagate through base metal, not just welds. The 19 complete hull failures proved that welded construction requires crack arresters. Each disaster advanced understanding, each death purchased knowledge. That is the cost of innovation under pressure. The Liberty Ship program succeeded because America could afford to fail. When a ship broke, another launched. When a design flaw killed sailors, engineers modified the design and kept building. The arithmetic was brutal but effective. Build faster than ships sink, learn faster than ships break, improve faster than enemies adapt. The Maritime Commission received more than 3,000 improvement suggestions during the war, which collectively saved $45 million and 31 million labor hours. 3,000 ideas, not from corporate research departments or university laboratories, from shipyard workers who saw better ways and implemented them. That is the illegal trick. Not any single innovation, but the systematic embrace of continuous improvement by people who had no formal training and every reason to believe the task was impossible. The title promised 72 hours instead of 6 months. The reality: the first ships required about 230 days to build. The median production time per ship dropped to 39 days by 1943. Not 72 hours, that was the Robert E. Peary publicity stunt, with much work remaining after launch. But 39 days, 1/6 the original time. A 6-fold improvement in construction speed while simultaneously implementing design modifications to prevent catastrophic fractures. 6 months became 5 weeks. That is the true story. Less dramatic than 72 hours, but far more remarkable because it was sustained across thousands of ships for years. And it happened because a welder at Richmond Yard No. 2 invented a cast-iron tool that looked like a femur and eliminated 1,200 clips per ship. Because another worker designed a prefabrication plant that reduced engine installation time by 90%. Because Constance Tipper proved that steel itself, not welding, caused brittle fractures. Because engineers installed riveted crack arresters when theory failed. Because merchant mariners sailed on ships they knew might break, because the alternative was losing the war. The illegal trick was the audacity to attempt the impossible, and the wisdom to learn from failure fast enough to succeed before the mistakes killed too many people. It did not always work. 10 men died on the John P. Gaines. Over 9,000 merchant mariners died during World War II. Some died from torpedoes, some from mines, some from aircraft, and some died because their ships simply broke apart in cold water, victims of material science that no one fully understood when construction began. Their deaths were not meaningless. They purchased knowledge. They forced improvements. They created the discipline of fracture mechanics and advanced welding techniques and better steel specifications that saved uncounted lives in the decades that followed. That is the cost of innovation. That is the price of building faster than you understand. That is what illegal trick actually means. Accepting known risks because the alternative is worse. 2 Liberty ships remain operational today, SS John W. Brown and SS Jeremiah O'Brien. Both are museum ships that still put out to sea regularly. 2 ships out of 2,751. 0.1% survival rate. The ships are gone. But what they taught remains. Every welded bridge, every modern cargo vessel, every rapid construction project, every diverse workplace, every engineer studying fracture mechanics. The legacy is not steel. The legacy is knowledge purchased at the cost of 10 lives on the phrases. John P. Gaines, preserved in 2 museum ships still powered by obsolete steam engines, and embedded in every structure built using techniques pioneered by workers who learned to weld in a week. The morning of November 12, 1942, 4 days and 15 hours after its keel was laid, the SS Robert E. Peary stood ready for launch, proof that American industry could accomplish the impossible. Not because of one illegal trick, because of 3,000 legal improvements implemented by people who refused to accept that faster was impossible, because Garrie Thompson invented a better way to hold steel plates together, because that innovation, multiplied across thousands of ships and millions of hours, helped win a war. That is the story. Not hyperbole. Just history, properly understood. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.